Good afternoon, everyone. Thank you, Pierre. Like you said, I am the head of data science team at SNCF Réseau. So SNCF Réseau is a French company which is responsible for maintenance, operation, and development of rail infrastructure. Today, I'm here to discuss how advanced tools and methods can transform rail asset management, helping us predict and prevent costly failure before they occur. Our scope cover critical areas such as track infrastructure, rail, ballast, switches, signaling, signaling, electrical system like catenary, substations, and bridge and tower. Tunnels, sorry. Did you know that a high percentage of rail accidents are caused by failure infrastructure? Whether you are on maintenance or operation or even in management, um, the impact of unplanned downtime affects us all. So we have to reduce that number significantly to improve safety, to reduce impact of delays and reduce accidents, and to obtain customer satisfaction. That's where advanced predictive tools come into play. Today, I'll introduce powerful tools and methods to prioritize the regeneration of railway assets, ensuring that we intervene at the most critical moment to prevent failure. Today, it's difficult to have this level of precision due to numerous criteria and constant involves, but with our methods, they can help us to predict and to prevent failures. So let me now walk you through the methods and tools we are using and explore how this works and the benefit it offers. First, for inputs, we need some data inputs, so infrastructure data, some results of aging law or survival analysis, maintenance data related to maintenance costs and renewal costs, impact on regularity, and other related data. Second, we need to implement methods and algorithms. So we have to define the methods we need. I will talk about it later. And then for outputs, for the results, we need to tailor the results to the supervisor's specific needs by proposing a set of regeneration scenario. For this, we have two methods. The first one is to prioritize what needs to be done using multi-criteria optimization. So we have the two methods, critic and TOPSIS. The second one is use of generative intelligence, artificial intelligence to generate maintenance schedule. The second method is under development, so we don't have results yet, but let us focus on the first one. The steps of the methods are: first, establishment of an investment program to be evaluated. Second, identification of investment valuation criteria. Third, quantifying the performance of investment according to the selected criteria. Four, to aggregate the performance of investment according to the selected criteria. And five, to prioritize investment. So let's break down this point concretely one by one. The first topic to establishment of an investment program to be evaluated relies on survival analysis. So this analysis, the use of this analysis is crucial because it informs us where and when to allocate resources most effectively. By understanding how long assets are likely to function before failure, we can prioritize maintenance and regeneration effort more effectively. So these graphics show the survival curve of two substation circuit breaker, two different circuit breaker. It illustrates the probability of an asset functioning over time without failure. The curve typically starts at 100% of functioning, or one for probability, indicated that all assets are operational and decreases as time progresses, reflecting the likelihood of assets failing as they age. So I said that these graphics show the survival curve of the two substation circuit breaks, and this decreases as time progresses, reflecting the likelihood of asset failing as they age. For example, here the curve indicates that assets perform well until the age of 20. I don't know if it's clear. The first one, the age of 20, we can say it here. The curve decrease, and here over the age of 14, the curve decrease, and here we say that the survive indicator is 60%. So we can say that these two ages are the age critical, after that the failure become common, most common. So for each asset, we put the age and the remaining useful life in front of each asset. The second and third point is to select criteria with expert. So here we selected the age, the remaining useful life, failure rate, risk function. These are criteria results of survival analysis. And then also we decided to add the ratio of corrective maintenance cost by remaining useful life. This metric is used to evaluate the cost effectiveness of maintaining the asset. A high ratio indicates that the cost of maintaining the asset is high relative to the time it will continue to function. So it's recommended to replace the asset rather than to continue repairing it. A low ratio is justified to continue with corrective maintenance. So after gathering all the data, we need to aggregate this value by asset into a single value. It's represent the overall score. This score will make it possible to compare between all investment programs. To do that, we have to calculate weights of criteria. Here we are going to use the critic methods. Critic is criteria importance through inter-criteria correlation approach. So how does it work, the critic methods? First, we normalization of data. Second, calculate standard deviation. Then to calculate correlation between all criteria. And then to calculate information quantity of each criterion. The objective is to have the information that each criterion give to the whole criteria. And it's a combination between correlation and standard deviation. Then finally, we calculate weights by applicating these rules. So the next step is to multiply these weights by all the values data gathering in this table. So the last methods to apply is the TOPSIS method. It's a technique for order of preference by similarity to ideal solution. This method calculates two solutions, the ideal and negative ideal solution. So the ideal solution is the best possible value for each criterion is the optimal scenario. And inversely, -1 has the worst scenario. So here, to calculate the best solution, it's the I plus, and it's the minimum of the age. We said that it's the best solution. So it's the minimum of age, the maximum of remaining useful life, maximum of failure rate, of risk function, and the ratio. And here, the negative ideal solution, so the worst scenario, is the maximum of age, minimum of all other criteria. So the objective of these methods is to calculate the Euclidean distance between all these alternative solutions, the blue represented by the blue points, the distance between these blue points and the ideal solution represented by the green one, and the negative ideal solution represented by the red one. So finally, rank the solution by their value. The highest value is considered is the best one. Here we can see first operation, the first recommended operation, followed by the second one. So calculated by this distance, Euclidean distance between the point I shown before. And this is the second one, and so on. So with this result, we offer to experts insightful planning for intervention. They validate the operation by considering other criteria like feasibility and implementation costs. So these are the final results, but we are working on improve this result by adding some other algorithm and constraint. For example, here we can incorporate additional criteria and introduce further optimization with constraint. By application, the first rule, if we take an example that the global budget is equal to C, so we have to find the operations respecting this condition. Also, in parallel, we are exploring generative artificial intelligence methods. Earlier, I talked about it. It's under development, but we are focused on studying this solution to generate maintenance schedules program to supervisor. So based on historical data of schedule maintenance.